Hello everyone, we are back with chapter 6 of this GOB or Chem 51 class, and the contents of this lecture are going to be an introduction to the mole, atomic and molar mass, what they are and how you would calculate them. We'll look at how to perform a mole to mass conversion, a mole to mole conversion, and finally a mass to mass conversion. So without further ado, what is the mole? Mole is a certain number of molecules, pure and simple. So if we look at this cartoon here, we can see a certain number here, two hydrogen atoms plus one oxygen atom gives one unique compound called water. So we can say that two objects plus one object gives another unique object. Instead of just saying object, we can say 2 moles of hydrogen plus 1 mole of oxygen gives 1 mole of water. Conversely, we can double everything up. So rather than 2, we can say 4 moles of hydrogen. Rather than 1, we can say 2 moles of oxygen. And then rather than 1 mole of water, we get 2 moles of water, etc. The mole is numerically equal. So humans decide what we mean by mole. We set mole equal to a number called Avogadro's number, which is 6.022 by 10 to the 23. So humans have invented this relationship between mole and Avogadro's number, but Avogadro's number itself is not invented. It's a physical number that's out there in the universe. There is no way that aliens would know that Avogadro's number equals 1 mole, but aliens would discover Avogadro's number because it's the ratio of two fundamental constants of nature. The derivation of Avogadro's number you will probably encounter in a different chemistry course than this one. But essentially it's the ratio of Boltzmann's constant with Avogadro's number. And I believe historically it came from Einstein's study of Brownian motion. So we set Avogadro's number equal to a mole, so that if I go back and I now look at 2 moles of hydrogen, that means 2 multiples of Avogadro's number. 1 mole of oxygen means 1 multiple of Avogadro's number. 1 molecule of water as a product means 1 multiple of Avogadro's number. What else should we say about Avogadro's number? The other thing we can it's probably on the next slide, but one thing we can say about the mole is, so Avogadro's number is the real thing. Humans set that equal to something called a mole, and the prefix mole, or the word mole, is the prefix of molecule. So it's just associated with a number, specifically Avogadro's number. So it becomes useful when we quantify chemicals, because like anything small, you quantify based on mass, and we're essentially in the next slide going to link number or Avogadro's number to a mass. And practically we're going to weigh to obtain a number. Okay, this is a useful triangle. If we start in the top, we have number of moles, which we'll call n, lowercase n. If we want to convert moles to number of molecules, capital N for number, we would multiply by the molar mass, symbolized here as mm. So this is just the mass of 1 mole. And if we go backwards, we do the opposite argument. So the opposite of multiply is divide. So we would divide by molar mass. We'll look at molar mass or molecular mass, as they call it here, in a second. But it's essentially just the mass of all the constituent elements in the molecule. We add those all up to get the molar mass or the molecular mass. If we want to go from moles to the mass in grams, which here they've called weight, then we would multiply by molar mass. And then if we want to go back from the mass in grams or the weight to the number of moles, we will divide by molar mass. And then finally here we've got mass in grams to number of molecules. Again, we can go back and forth between mass and number or mass and moles. Okay, let's look on, okay. So the atomic mass or molar mass, this is what we were saying in the previous slides. So essentially it's the mass of the molecule. So by definition, the mass in the periodic table of each element has an abstract unit called atomic mass unit. If we just literally replace that label atomic mass unit with the label gram, that defines exactly 1 mole or Avogadro's number of that material. So for example, if you look at the periodic table at copper, let's say the copper has a mass, an atomic mass unit of 63.546. Therefore, if we go to the lab and we weigh out 63.546 grams of copper, that's exactly 1 mole of copper, or 6.022 by 10 to the 23 atoms of copper. Okay, so here we've got an example calculation of the molar mass of copper 2 phosphate, the structure is shown here. So we have 3 copper atoms, so 3 multiples of this mass conversion to moles. Phosphorus, we have 2 phosphorus, so 2 multiples of the phosphorus mass. And then finally 8 oxygen, so 8 multiples of the oxygen mass. We add them all together, and we get this value here. Remember the dashed line. This gives us the difference between significant digits on the left of the dash, insignificant digits on the right of the dash, so that we're not prematurely rounding the number. So we can get the mass of 1 mole of this compound by adding the constituent elements. Okay. You can hear crows after crows crowing right outside my window. Very Viking ravens, what have you. Okay, atomic mass and molar mass. We can say molecule, so you can have 2 carbon atoms in a balanced equation. We can just say that rather than 2 molecules, that's 2 moles of 2 moles of the element, or 6 atoms, we can interpret that as 6 moles. 1 atom, we can interpret that as 1 mole. And the benefit of the mole, it immediately allows you to convert that to gram, whereas just molecules, it's a bit more awkward to do that. But this unique value of mole, this large scaling, because of the factor of Avogadro's number, it lends it into a region that we can weigh out in the lab in units of grams. Once we know how many moles of an element we have in a compound, so here C2H6O clearly has 2 moles or 2 molecules of carbon in it, we can set that equal to a ratio. So either the 2 moles of carbon as a numerator or a denominator, and we call these equalities because they're just 2 expressions that are equal to each other. And then we can use those expressions in calculations. So here's this triangle that we saw in a couple of slides ago. And we're going to now start to look at our mole conversions. So in this slide, we're going to look at mole to mass conversions. So as the cartoon shows, once we have moles of substance, we can convert it to mass of substance by using this conversion between mass and moles that we saw by definition in the previous slide. And we can go back again by taking the inverse relationship, because remember, in the previous slide, these equalities, or the inverse equalities, they're basically fractions, and all that matters is that the numerator and denominator are equivalent in the given expression. Okay, so here's an example of a calculation. We have a balanced equation. So calcium carbonate and 2 lots of HCl gives calcium chloride and carbon dioxide and water. And here we're going to convert moles of HCl, which is a reactant, into grams of CO2, which is a product. So to construct this, I recommend you to construct it backwards. So if we want grams of CO2, we immediately write the formula rate of the molar mass. Get used to people saying the same thing in different ways. So molar mass, formula rate, molecular mass, they all mean the same thing. And I'll use them interchangeably just to get you used to the different ways of saying the same thing. So I need grams of CO2, so I write grams of CO2. What grams do I use? I use the grams of the molecule. So I look at the periodic table at the mass of carbon, which is about 12.01 grams. I add the mass of 2 oxygens, which are about 32 grams total. So 32 grams plus 12.01 grams. This is the origin of this 44.01 grams. And by definition, I set the mass of the whole thing in moles. Sorry, the mass of the whole thing in grams equal to 1 mole. Then I promote the denominator unit, mole of CO2, up to the preceding numerator. So I have moles of CO2, and then I use the balanced chemical equation. I know that 1 mole of CO2 is equal to 2 moles of HCl. So this equality comes from the balanced chemical equation. So now you can see if you don't correctly balance the equation, you're in a bad place, and none of your calculations are going to make any sense. So we've got this 1 to 2 mole conversion from the balanced chemical equation. The denominator, moles of HCl, becomes a preceding numerator, moles of HCl. And then I have my input, which is 2.09 moles of HCl. Where did that number come from? We just made it up to show you how to do it. No big deal. We run this through 2.09 multiplied by 1, multiplied by 44.01, divided by 2, divided by 1, equals 46.0 grams of CO2. So we have successfully converted moles of a substance to mass of another substance. Next, we're going to look at something that is arguably a bit simpler, just mole to mole conversion. Here we just need the balanced chemical equation. So here we have an equation that's very important. It's called the Haber-Bosch process, which is arguably chemist's most important equation. But that's for another time and another story. So we have 3 moles of H2 and 1 mole of N2 gives 2 moles of NH3 or ammonia. And for a given mole input of H2, what's the output moles of H3? So we write down the target unit, mole of NH3. We immediately write moles of NH3 again to preserve the equality we've written. From the balanced equation, 2 moles of ammonia equals 3 moles of H2. So we set 2 moles of ammonia equal to 3 moles of H2. Moles of H2 becomes the preceding numerator, so we can cancel the units. And then we've got our arbitrary input of 33.9 that we just made up. I have a lot of students say, well, where did 33.9 come from? We just made it up. If we change 33.9, we would change the output moles. No big deal. So we multiply 33.9 by 2, divided by 3, and we get our output 22.6 moles of ammonia. Finally, in this lecture, mass-to-mass conversion, arguably the harder of the 3, just because it's longer. You know, when I say hard at this level, I just mean long number of steps. So maybe hard is not the issue, maybe complexity is the issue, because that tends to correlate with number of steps. But anyway, we have a balanced equation. It looks like a combustion reaction. So we have octane, or CH18, plus 25 moles of oxygen, gives CO2 and H2O. And notice our plan here, where our input is grams of a chemical, we convert that immediately to mole. We relate the moles of that to the mole of our known, and then we spit back out grams at the end. So notice we can't go directly from gram to gram. We have to essentially do the traveling in the mole mobile. So we have to, similar to when you get on a freeway, you can't really run down the freeway. You have to get in your car, drive down the freeway, and then get out your car again. So here, the car is just a mole vehicle. Okay, so we're asked how many grams of O2 are produced from 342 grams of octane. So let's construct it backwards. So grams of O2, this is pretty rounded, but so don't really read too much into the rounding here because we've heavily rounded, but just look at the procedural aspects of the calculation. So grams of O2, we have grams of O2, 32 grams of O2, that's roughly twice the elemental mass of oxygen. We set that equal to a mole. The denominator here is the preceding numerator. This 25 to 2 mole ratio comes from the coefficients in the balanced chemical equation. There are 25 moles of oxygen in the same balanced equation as 2 moles of octane. That's where that ratio comes from. Then the denominator unit is the preceding numerator. So I have moles of octane as a numerator here. By definition, a mole is the weight in gram. So we take 8 carbons, 18 hydrogens, add them all together, and horribly rounded, that should be 114. The denominator here becomes the preceding numerator, and we just have a random piece of input that we just made up. Again, most of my students fret about the origin of the input data. It was made up in this case. So multiplying through, we have 342 multiplied by 1, multiplied by 25, multiplied by 32, divided by 1, divided by 114, divided by 2, divided by 1, equals, in a horribly rounded way, 1200. So order of magnitude, that's fine. Just showing you how to do the calculation, it's fine. We'll worry about sig figs clearly in another video, but that's the general procedure of how to do this. So take home for mass to mass conversion, you have to immediately convert to moles, do the mole conversion, and then convert finally to mass. Don't try and go to mass already. Here is another example. How many grams of HCl are produced by the reaction of 100 grams of CCl4? We have a balanced chemical equation here. We have our plan here, mass converted to moles, mole ratio used to convert to moles of the other chemical, and then finally back convert to mass at the end. So we'll construct this backwards. So we've got grams of HCl. We know that grams is equal to moles. So 1 mole of HCl is 36.46 grams of HCl. We multiply that by the mole ratio. So we have this 4-to-1 ratio from the balanced chemical equation. So HCl is 4 and CH4 is 1. We have this 1-to-4 ratio. Then I know that a mole of CH4 is 16.05 grams of CH4. Where did the 16.05 come from? Well, that's just one carbon atom, 4 hydrogens added together. The AMU is just relabeled as gram. And then finally, our input is 100 grams. Multiply that through, and we get 908.7 grams of HCl. So that was short and sweet, and that will conclude the video.